So I'm going to talk today about how developing open source Python 3 tools can really allow us to look into the advantages and disadvantages of different methods of determining PTX conditions in igneous systems. So I'm going to talk about three main methods which are widely used by petrologists. The first is melt inclusion barometry. So using the concentration of water and CO2 along with the major element content of the melt to work out the pressure at which this melt inclusion was trapped. The second is using composition of minerals with or without melt to calculate pressures and temperatures and sometimes water content in igneous systems. And the third is fluid inclusion barometry, so using the density of CO2-rich fluids to calculate the pressure at which that pocket of fluid was trapped. And three open source Python tools have been developed to help address these problems. So for melt inclusion barometry, we have Vesical. For mineral melt barometry, we have Thermobar. And for fluid inclusion barometry, we have DiodFit, which can be used to process both microthermometry and Raman data, including spectral fitting. So before these Python tools exist, what was the state of the field? Well, let's look at CPX liquid barometry as an example. So this is the spreadsheet that you could download from Keith Peterka's website. And you would take your liquid composition and you would paste it in, and you would take your clinopyroxene composition and you would paste it in. And this would require you to reorder your electron microprobe data in the order that's defined by this spreadsheet. So that will give you all of Keith's models. If you then wanted to use Maurizio Petrelli's machine learning method, you would have to download his Python file. And you can see here, this requires you to input your liquid data in a certain spreadsheet format between, in this case, columns B and M. And then some other tools are available in R, some might require MATLAB, etc. So if you want to compare lots of different models, you're going to have to download a lot of different spreadsheets and scripts and have knowledge in all of these languages. Many of the more complicated calculations, so for example, melt inclusion saturation pressures and equation of state calculations, actually require users to type in numbers for each calculation. So for example, if you wanted to use the solubility model magma-sat, you would have to type in the major element composition of each of your melt inclusions, the volatile content, and then press compute to calculate the pressure. And the same was true for the Iacono-Marziano solubility model. So if you have 100 melt inclusions, this gets tedious pretty quickly. And the real problem comes is if you want to propagate uncertainty using, say, Monte Carlo methods. You can't easily input 10,000 simulations to look at the effects of varying one parameter and the errors that result from your analysis. So what can Python tools allow us to do that's different? Firstly, we can make that user input more simple. So simply, people load in a spreadsheet. It has certain column names. They don't have to be in any order. So the code is looking for the column silica rather than wanting it to be in a certain place. And you can load in as many rows as you want. You don't have to do each calculation one at a time. You can do 10, 100, or 1,000 calculations automatically. These codes also allow you to compare the different models for a certain type of calculation. So for example, say you're interested in saturation pressures in a morgue basalt, and say you measure 0.2 weight % CO2. You might be interested in what pressure that corresponds to, but you have to choose which solubility model to use. Well, in Vesical, you can easily and very quickly produce these trends showing how pressure relates to CO2. And being able to produce this graph shows you that actually there are big differences between choosing the propagate and the magma-sat solubility model. And that choice results in a large systematic error in your calculated pressures. Similarly, for CPX liquid barometry, let's take 4 experiments which were done at 4 kilobars, which is the pressure shown by the red line. And many different barometry and thermometry equations are used in arc basalts, for example. Each of those different equations is shown in a tick on the x-axis. And again, this allows you to see that actually the pressure that you get is highly dependent on your model choice. So you could go from thinking magmas are stored at about 15 kilometers down to 60 kilometers just based on the model you choose. Now, these can be very easy to compare because, for example, in Thermobar, if you want to use one equation for pressure, you would simply type this. And if you wanted to change it and use, say, the Neve barometer, you just enter a different, what we call string, this basically set of letters. And that is very much easier to flip between models than changing spreadsheet or changing code. The other thing that these tools allow you to do is propagate uncertainty. So for example, when we measure clinopyroxene on an electron microprobe, it reports a given value. But there is obviously precision associated with that measurement, and the microprobe will actually tell you what the % error is on that measurement based on the counting of X-rays. So for example, say you measure a clinopyroxene, we can simulate what the spread of possible values would have been just because of counting statistics. And we can make synthetic clinopyroxenes following this distribution we would expect from analytical uncertainty. And we can do this for every single oxide. And then we can take our synthetic simulations and we can calculate pressures and temperatures for them. And this is what we see. So this is Monte Carlo simulations for, say, if you had a homogeneous CPX and you repeatedly measured it with an electron microprobe. So we can contour 95 and 67% of simulations. So what this shows is this spread in pressure and temperature, so between 0 and 4.5 kilobars, can be generated just by the precision of your measurement. And most importantly, the uncertainty when propagated produces this increase in temperature with increasing pressure. And these arrays have been interpreted many times in the literature as transcrustal storage. If you want to invoke transcrustal storage, you have to show that your spread of pressure and temperature in your system greatly exceeds the spread that would be caused just by the propagation of your input uncertainties. Now, we can do this for the three methods we're talking about here, and that really allows us to compare the precision of different ways of determining magma storage depths. So, for example, here we're showing the 1 sigma uncertainty for CPX only and CPX liquid barometry for typical electron microprobe conditions. We're then showing the uncertainty propagated for melt inclusion vapor bubbles, and that error bar basically results from the measurement of the volume of the vapor bubble when we're using Raman spectroscopy. And then the third one is looking at the pressure distributions of fluid inclusion. So this is uncertainty in the CO2 density by microthermometry, or in this case, Raman spectroscopy, and the uncertainty in the entrapment temperature of that fluid inclusion. And this, for example, allows you to see that in terms of precision, fluid inclusions are far more precise than these other methods. So you might say, well, what if I can't code in Python? How are these tools useful for me? We have tried to make these tools as user-friendly as possible. So for example, say you want to take a fluid inclusion density and convert that into an entrapment pressure. You would simply load in an Excel spreadsheet, and then the function you're using is this calculate pressure for a given row and temperature. Now, there is complicated Python code behind this, and if you're interested, you can certainly dig into that on the GitHub page. All of this code is open source. But for most people, they don't care exactly how we're solving for pressure, for example, knowing density and temperature. All they want to do is be able to use this in their system. And the point is, all of this code is wrapped up in these functions. So in reality, all you have to do is load in a spreadsheet where you have your estimate of the entrapment pressure and your density. You're using this function and you're simply telling it, okay, I think it was trapped at this temperature in Kelvin, where you just tell it the column heading for where you're reading from. Similarly, you simply tell it what column you are storing your CO2 density in. You are then telling it what equation of state you want to use, so you can easily compare different equations of states. And then just to get a nice output, you're telling it where your sample name column is. And it will output a spreadsheet-like format where you have your pressure calculated. So again, you could use this to run 1,000, 10,000 different fluid inclusion pressures and to propagate uncertainty. So for all of these tools, we've written examples as Jupyter notebooks. So these are very, very easy to read examples, all hosted on the internet through Read the Docs. And we've also made numerous YouTube tutorials doing worked examples. So really the idea is these tools should be being able to use by anyone, even if they don't know how to use Python. So with that, I'm happy to take any questions.